For our project, the main hardware component that makes up the wearable computer is the Raspberry Pi 4 kit along with the input and output peripherals. The Pi is reasonably faster and runs with a speed of 1.5 GHz. The Pi weighs 10.7 ounces, which is pretty light, and it's an advantage as it's intended to sit on the side of the cap. The hardware component works as a client which communicates with the Google Cloud Server using three main application interfaces: Google Speech API, Google Vision API, and Google Text-to-Speech API. The Pi is operating on Wi-Fi, which provides it with a better connection, a better range, and most importantly provides it with a wireless network security as opposed to other methods such as Bluetooth. The total cost of our project was $30.82, which falls within our overall budget of $250. Now we'll have a look at individual hardware component and how they interact with each other. This is the Raspberry Pi 4 model with a 4 GB storage capacity and USB 3 support, which means faster input and output connection once the peripherals are connected. The Raspberry Pi connects with 3 input devices and 1 output device. The first input device is the Pi switch component, which turns on the Pi. The Pi auto-runs the project file every time with startup. This is done by setting the absolute path to the project directory in environmental variables. Once the Pi is running good, our second input device, the USB connected microphone, waits for the user input. The user speaks into the microphone, passing a command either asking to know what is ahead of him or to detect an object or a facial expression. The streaming application interface, used by the Google Speech API, records this command from the user with the help of a Pi audio module and waits for our third input device, the camera. The camera captures an image of the area in front of him or her for further processing. This image is sent to the Google Vision API to extract image details from the picture in relevance to the commands given. The results returned by the Vision API are in text form, so the Google Text-to-Speech API converts these results to a speech form and executes the results through our output peripheral device, the computer speakers. The visually impaired person can now listen to the speakers to find out how the environment looks in front of him or her.
The housing unit for the hardware component is crucial as the user will be interacting with this aspect of the design. Two major requirements while designing the product was usability and functionality. In addition, the appearance was also taken into consideration such that the final product not resemble an assistive device. As a visually impaired client would be utilizing the wearable computer on a frequent basis, it was imperative that the product be comfortable, easy to use, and reliable. Hence, a slide-on styled housing unit was created. The main purpose of the housing unit is to encapsulate the hardware components to make it wearable. The hardware components, once attached to the apparatus, can be slid onto the side of a cap. The user can then trigger the program with a push of a button and proceed to interact with the device using voice commands, thus making it functional and easy to use.
The Google Vision API is an essential component of the EyeCan. Google Cloud Vision enables developers to understand the contents of an image by encapsulating powerful machine learning mechanisms into an easy-to-use REST API. This is done by categorizing different images into different database categories and then taking similar images and comparing them to images found in Google's database. We have used this functionality to incorporate it into finding the different objects, logos, and facial expressions found within an image. For example, if the user inputs the keywords such as logo or brand, all the brands detected within the captured image are returned. Similarly, if the user says words such as label or environment, all the individual objects detected within the captured image are returned. Moreover, if the user inputs the keywords mood, feeling, or expression, all the different facial expressions detected within the captured image are returned. This is done by first finding the person's face within the image and then assessing the facial feature alignment to identify the different facial expressions. We have also incorporated functionality such to give feedback based on the facial expression. For example, if the person is found to be happy, the user is prompted to smile back. Moreover, if the user seems surprised, the user is prompted to ask them what may have caused them to be surprised. Moreover, if the person seems upset, the user is prompted to ask them if something is wrong.
Speech recognition begins with analog to digital conversion. The input analog signals are sampled into smaller digitized signals. Since the input of speech recognition is mainly the human voice, the way these algorithms are produced are just like how voice is produced in the human body. The input signal is firstly matched with phonemes, which are stored in the databases or dictionaries. These phonemes contain either voice sound, which are vowels, or unvoiced sound, which are consonants. Consonants including the S and TH sounds. Now, this basic approach has been greatly enhanced to use deep learning or recurrent neural networks. This approach uses feedback loops to predict what the user will say next based on what they have said before. And this allows for a very successful and correct speech recognition technology. Now let's see how the Google APIs work together in the EyeCan. Firstly, a microphone stream is initialized. This is a continuous loop, which is the listen command, and this ensures that whenever the user says something, it is taken as speech input and given to the Raspberry Pi. Firstly, the speech-to-text API is used by Google, and a result is returned, which is stored in the transcript variable. This transcript variable is compared with keywords. Keywords such as quit or exit will terminate the program, while keywords which are the command names will then execute the appropriate commands. Once the commands have been executed, a result will be needed to give it back to the user. Now, the result given back will be through the text-to-speech API. The text-to-speech API will first initialize parameters such as the gender of the output voice and also the language. Finally, the run quick start method will be used, and this method first synthesizes the text which is needed to be outputted to the user. Using the predefined API parameters, it creates a voice output, and then the voice output is then sent to the user through the speakers or the headphones. As you can see here, a user manual comes with the EyeCan. This is for the visually impaired population to help them remember the commands associated with the EyeCan. As can seen here, the original name is here while its Braille counterpart is right here. So for example, logo. The dots in the middle represent spaces. So space L, space O, space G, space O. When the user feels this text, they'll understand that this is a logo command. So on and so forth for the rest, so they'll always be able to remember the commands.
Welcome to EyeCan. Please state a command.
If the user inputs the keywords read, reader, word, or words, then text recognition is done.
Words.
Initiating text recognition. Text detected in the picture are wearable computer for the visually impaired. Please state a command.
I wonder how my friend is feeling.
Initiating emotion recognition. The emotions shown are anger, very unlikely. Joy, very likely. Surprise, very unlikely. They seem really happy to see you. Maybe smile back? You may now input another command.
I would like to know the expression of my friend.
Initiating emotion recognition. The emotions shown are anger, unlikely. Joy, very unlikely. Surprise, likely. They seem surprised, perhaps ask them why they're so shocked. You may now input another command.
I would like to know the logo of this bottle.
Initiating icon recognition.
Keep it a little further.
Icons detected in the picture are Johnson's baby. You may now input another command.
I would like to know what is in my environment.
Initiating object recognition. Objects detected in the picture are white ceiling, black light, wall, room, line, house, stairs, floor. You may now input another command.
Thank you for your help. Quit.
Together we can say EyeCan. Goodbye.
Bye!
Good job, guys.
This concludes our capstone presentation. Thank you so much for watching. We hope that this video brings awareness on the visually impaired population, and we hope that our device can truly allow them to say, I can.